Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the polytropic process. Now what is polytropic process? We have already studied the process, is V is constant. This is isochoric process. We have already studied it. Then we studied P is constant. This is isobaric process. Then we studied PV to the power 1 is constant. This is isothermal process. Then we studied PV to the power gamma is constant. This is adiabatic process. This gamma is obviously Cp by Cv. Okay. Now, what if any process is PV to the power n and that is constant, and n is neither 0, which is if n is 0, then the process will be isobaric. If n is not 0, if n is neither infinity, because if n is infinity, the process will be isochoric process. If n is neither 1, so this is n is 1, isothermal process, and n is neither gamma, so this is adiabatic process. So n is neither of any one of them, so this is some other process, and we categorize this process as polytropic process. So this is the polytropic process, and obviously if we see the relationship of this curve, then if we check that if n is positive, then this is inverse relationship, and for that inverse relationship this curve would be hyperbola. Okay, but if n is negative, then it depends on the fact that what is this relationship. So we cannot name the process, or we cannot name the curve directly. So the slope of this curve, so obviously we cannot draw the curve because we do not know that what is the value of n. So the slope of this curve will be minus of n p by v. You can just replace the value of gamma from n, as we have already done in adiabatic process. The bulk modulus of polytropic process beta will be dp by minus of dp by dv by v. So it would be equal to n into p. This would be the bulk modulus. Compressibility will be 1 upon bulk modulus, and hence it would be 1 upon np. This is the compressibility. And if we talk about the work done, so work done in adiabatic process was 1 upon r upon gamma minus 1. It was r upon 1 minus gamma P2 V2 minus P1 V1. It was for adiabatic process, but in place of gamma we have to replace n. So for this polytropic process, the work done is r upon 1 minus n into P2 V2 minus P1 V1. Or in other words, I can say that work done will be r upon 1 minus n into this n is number of moles. Let us denote it as number of moles, and this would be T2 minus T1, because we have replaced P2 V2 by this R would not be there, this would be 1, and here it would be, we have replaced P2 V2 by nR T2 and P1 V1 by nR T1. So this n is the number of moles. I am not using the small n because small n I have already used as polytropic constant. So this is the work done in this process, and the most important thing in the polytropic process is the specific heat. So let us discuss the molar specific heat in polytropic process. So molar specific heat can be derived by first law of thermodynamics, which says that dq will be equal to du plus dw. Now dq will be nc dt, du will be ncv dt, and dw is n. This n is the number of moles. Again, this is the number of moles, or if we wish to write it down as capital N, we can do it in all the three terms. So this is n, this is n, and this is n, and r upon 1 minus n into delta t, so dt. And you should always remember that dt is t2 minus t1. Okay, so this is if we cancel out n dt in all of these three terms, then c will be equal to cv plus r upon 1 minus n, and cv is r upon gamma minus 1 plus r upon 1 minus n. This is the value of molar specific heat for polytropic process. You can also check it for all other processes. If n is equal to 0, we know that if n is equal to 0, it was isobaric process. So if n is 0, we can see that c will be equal to cv plus r, so that is cp, or I can write it down here. If n is equal to infinity, that was isochoric process. So in isochoric process, if you substitute the value infinity here, then 1 upon infinity will be 0, so c will be equal to cv. And if n is equal to 1, that was isothermal process. So if you substitute n is equal to 1 here, so c will be equal to infinity. We know that. For isothermal process, the specific heat is infinite. And if n is equal to gamma, okay, so if n is equal to gamma, then we can see that it would be c will be equal to r upon gamma minus 1 plus r upon 1 minus gamma, so it would be 0. Okay, so this was the specific heat for polytropic process. And if we talk about gamma, and gamma is the volumetric expansion coefficient, so it was dv by v dt, and we have already derived the value of gamma for adiabatic process. It was 1 upon t into gamma minus 1 with a negative sign. This gamma is cp by cv, and this gamma is adiabatic volume expansion coefficient. So we can replace the gamma by n, so it would be 1 upon minus 1 upon t into n minus 1. This is the value of volumetric expansion coefficient for the polytropic process. So this was the complete information about the polytropic process, and in the next video I'll be bringing the free expansion in detail. Thank you.